Yeah.
Hello everyone, welcome to our lab number 3. For the introduction, today we're presenting our acceleration experiment using a glide car connected to a hanging mast. The main object of this lab was to master the capstone, graphical presentation tools and data, gathering techniques while applying Newton's second law to determine acceleration, and we compare theoretical acceleration with three experimental methods and analyze the percent error. And in theory, acceleration depends only on the net force and total mass of the system. The question we would use was,
For this experiment, we used a glide card, a pulley system, a string connecting the card to a hanging mast, a motion sensor, a balance to measure masses, and the capstone software for the data collection. First, we measure the masses using the balance. The mass of the glide card was 178 grams or 0.178 kilograms. The mass of the hanging weight was 6 grams or 0.006 kilograms. The motion sensor was placed in front of the glide, and we made sure it could continuously detect the car during motion. We did not use the full length of the track, only the length determined by the spring connected to the hanging mast. Before running the experiment, we calculated the theoretical acceleration using Newton's second law. Because the velocity became more negative during motion, the car accelerated toward the sensor. Therefore, we use this formula.
Yeah.
Since the car was accelerating towards the sensor, we use a negative gravity that is minus 9.8 meters per second squared. And this is the formula that we use, that is acceleration is equal to the mass of the weight, that is 0.0006 kilograms, times the gravity, and then we have the mass of the weight, that is again 0.006 kilograms, plus the mass of the car, that is 0.178 kilograms, and our final acceleration was negative 0.320 meters per second squared.
Experiment development. We will find experimental acceleration in 3 different ways. From the position versus time graph, from the velocity versus time graph, from the acceleration versus time graph.
So this is our method 1 for the from position versus time graph. So for initial velocity, we had negative 0.08 meters per second at 0.2 seconds. For our final velocity, we had negative 1.05 meters per second at 1.4 seconds. So here's our formula, which is final velocity minus initial velocity, and this is our final time minus our initial time. So for final velocity, we had negative 1.05 minus, which is the initial velocity, which is negative 0.08. And for final time, we had 1.4 minus 0.2, which is our initial time. So at the end for acceleration, we got negative 0.808 meters per second squared. So for method 2, from velocity versus time graph, we added a new graph page in Capstone and selected velocity as a measure of the linear region of the graph and calculated the slope. The slope represents acceleration directly. So the second acceleration, we got negative 0.81 meters per second squared. So in method 3, from the acceleration versus time graph, we added another new page and selected acceleration as a measurement. Using the highlight tool, we selected the constant region and used the statistics tool to compute the mean. So mean acceleration was negative 0.93 meters per second squared.
At the top graph, the one that is in red, we can see that the red line is curved, which tells us the car was accelerating. If it were moving at a constant velocity, the line will be straight. At first, the position increases, meaning the car moves away from the sensor, and then the graph reaches a peak, which represents a turning point where velocity became 0. After that, the position decreases, meaning the car moves back towards the sensor, and the curve shape confirms that a net force was acting on the system. Then the second one is velocity versus time. This graph tells us how fast the car was moving and in what direction. Positive velocity means the car was moving away from the sensor, and the slope of this graph represents acceleration. We notice some spikes and fluctuations, which were likely caused by tension changes, friction, or small disturbances. Because of this, we select the smoother sections of the graph to calculate acceleration more accurately. And the last one was acceleration versus time, the green one. Ideally, constant acceleration will appear as a straight horizontal line, but however, in this graph shows fluctuations around a value, which means small forces like friction and pulley resistance affected the system. So we use the highlighted tool to select the most stable region and calculate the mean acceleration. These variations help explain why our experimental value differ from the theoretical one.
Now we'll compare the theoretical acceleration, which each of the accelerations you compute. As we stated last slide, to compare two values is essential to do it as a percentage. In this slide, because we were comparing against a theoretical value, we will call it a percent error instead of a percent difference. Percentage error formula equals the theoretical value minus the experimental value divided by theoretical value times 100.
So the theoretical accelerations is equals to negative 0.320 meters per second squared. And for A1, we found that the error was 152.5%. And then for acceleration 2, we found that the error was 153%. And for the last acceleration, we found that the error was 181%. So we discussed where these percent errors should be similar, since all experimental values come from the same system, and they should be relatively similar and they are close to each other. However, they're not close to the theoretical value. And we then discussed where the error came from, and possible sources of error include the friction between the car and the track, the pulley rotational resistance, the string tension losses, and a resistance, sensor noise, human error selecting the points, and also the slight push when releasing the car. And finally, we conclude that the error cannot and should not be exactly 0 because real experiments always contain uncontrolled forces. And as a team, we define these holes. Good experiment, less than 20% error. Regular experiment, 20 to 50% error. And a bad experiment will be 50% error. So based on this scale, our experiment falls into the bad category because friction was not negligible compared to the small hanging mass. So if we had to repeat this experiment, we will choose a velocity versus time graph method because the slope directly represents acceleration and reduces multiple step calculation errors.